stack like I saw. You're
Perfect.
I don't believe so.
I don't want to say all of it comes for us all.
Yeah, that's why
Unclick. Yeah, you can unclick. That's okay.
Have it come back and just so like we can find this. You have to like
Press control.
your side seat is in the yesterday I think that's just like
Where did you get this? Yeah. Oh, it came
I think it's very small.
So hello everybody, thank you for coming back after lunch. Before starting with our invited speaker Chiaki, just a few announcements about the dinner tonight. So there is a dinner at 6:30 at our house. And this place is not very far from here, it's just south from campus. So there is a group meeting at 6:10-ish in front of the building and to walk together. If you join the Slack channel, so the communication will be handled there in case you have any questions, or you can reach the organizers. These are the shuttles that after the end of the sessions today will bring you back to your hotels. And there is a special one that from the Delta Hotel at 5:45 goes back here at Space Telescope. So you can come back here from Delta and then leave to go to our house together with the group who is meeting around 6:10 on the front. And did I forget something? No. Good. All good. Great. So these are all the things for the dinner, but please check on Slack in case you have any questions. And now I will find the slides. What's new? Oh, wait, I can do this. Wait. Okay, so the first speaker today is Jackie Kobayashi, and she will tell us about chemical evolution. Please, Jackie.
Thanks for the introduction. I also would like to thank to the organizer. Microphone might not be on. I would like to thank the organizer very much for inviting me to this excellent conference. I'm really enjoying a lot and learning a lot. I'm here until Friday all day, so if anyone wants to discuss more, please feel free to talk to me. Ryan Sanders already gave half of my talk, so, so I'm gonna tweak my talk a little bit to highlight how we can learn about history of the galaxies, particularly inflow and outflow gas by using chemical abundances. The galaxies form from cosmological initial conditions. We can simulate them in a computer solving gravity and hydrodynamics, assuming star formation and feedback. Once we form stars, we know very good what should happen in terms of nucleosynthesis. So different type of stars produce different elements on a different time scale. So therefore, not only the total amount of heavy elements, metallicity, but also elemental abundance ratio evolve as a function of time and redshift. So we can use all of this information to understand the history of the galaxy. This approach is called galactic archaeology, has been very popular for Milky Way, the galactic archaeology, but we can apply this to other galaxies now, thanks to the JWST beautiful data. So this chemical evolution equation is already also shown. So I'm going to highlight just saying the first three terms, metal ejection terms, depending on nuclear astrophysics, namely the nucleosynthesis yields. Also, for model galaxies, we have to know how many massive stars exist in the system we are thinking. In other words, initial mass function is a big assumption. Some elements, particularly iron, come from binaries, also neutron capture elements as well, but we actually don't know the physics of binaries so well, so we have to also assume some progenitor system for 1A and neutron submergers. And on the basis, all of these calculations depend on nuclear reaction rate. Some are still uncertain. I'm working on this field with my cross collaborator Amanda Caracas and Maria Lugaro, and that's with this team we got to this periodic table I'm going to show in a minute. The last three terms, I call them galactic terms. There are three ways to solve them. Number one, assuming instantaneous mixing approximation. By doing that, the calculation gets much easier. I can do this entire history of the galaxy just 1 minute on my laptop. So this is very easy. In this way, we can test various input physics very quickly. So still, this is very useful. Another way is still this is very cheap calculation, but including cosmological growth of galaxies, and then following chemical evolution. That's also possible, and these are semi-analytic models. Ideally, we would like to trace more detailed physics, and to do that, we have to have the hydrodynamical simulations coupling to the detailed chemical enrichment. So there are various simulations happening. I'm also working on this field a lot. In this way, this is the last one is the only way to trace inhomogeneous enrichment physically. This way, we can study the internal structures within galaxies, such as metallicity gradient. We could also directly compare to the IFU map of simulated galaxies. So this is what's happening now. So there are subcategories are people can learn the cosmological box. In this way, it's possible to trace large-scale structure formation together with chemical evolution. But in this case, the numerical resolution is not enough. So another way is go to the zoom-in simulations, focusing on particular galaxy initial condition, and then put more particles to increase the numerical resolution. So I'm going to show both cases in my talk. So let's start from the one-zone chemical evolution. In this case, the star formation history is constrained from independent observation, like age metallicity relation of stars, and then the most important one is the bottom-up metallicity distribution function. As a result, it's possible to predict time evolution of elemental abundance ratio, like this is one example of carbon. So this is one-zone chemical evolution model. So metallicity and time is coupled. So it's a one-to-one correlation. So strictly, time goes from left to right. The small dots here are called carbon-enhanced metal-poor stars, SEMP stars. We heard about this a bit. This is a signature of the first star enrichment. I'm not going to talk about this so much. So it's a tiny dots. excluding them, we know how much carbon to iron should be produced across metallicity and time. So I can do this many other elements, and these chemical evolution models can successfully reproduce many elements. Zinc is very important element. The zinc abundance is well estimated in the stellar atmosphere across the wide range of metallicity. It is constant relative to iron. So to explain this, we have to have energetic supernova explosion like 10 to the 52 ELG. We named them hypernovae. And this is particularly important for the production of zinc and cobalt. This is energetic explosions. I think progenitor system should be Wolf-Rayet. The envelope should be removed. So Wolf-Rayet is also important for this elemental production, I think, indirectly. So neutron capture elements are also well reproduced. The europium is one of them. Jan mentioned this yesterday. Neutron star merger only. That's not possible to explain this. Observe the color points. And I am assuming our process also happened in a small number of quark supernova. And this progenitor maybe also Wolf-Rayet stars before the explosion. The same model is plotted in a different coordinate. That's the one you have seen many times. Just I want to highlight the details. In each little box, the time evolution is shown. In the box, the most left side is time 0, Big Bang. The right side is 13.8 giga-year now. So you can see the little dotted line, the vertical one, that's the 4.5 giga-year ago when our solar system is formed. You can also see dotted horizontal line, that's the observed abundance in the solar atmosphere. So my lifetime goal is I want to go through this crossing point if I add all of the elemental abundance, all of the production side. So some key elements are good. I can highlight this oxygen, nitrogen, or iron. Manganese is also key element for type 1 supernova. These elements are very well reproduced. But some of them, you see some mismatches like gold. In my model, it's very underproduced compared to the observed value. So this was an interesting problem for nuclear astrophysics. So I'm talking so far, galactic chemical evolution models are useful to confirm nucleosynthesis of stars. After this, I'm also going to talk to you. Chemical evolution models are also useful to constrain formation processes of galaxies. To do that, I'm showing 3 distinct models here. The number 1 is a green one. Let's assume all gas is present to start with, and then you switch on the star formation and form stars. So in this case, you have a very starburst. Metallicity enhances very quickly in the green line. But if we count the number of stars at given metallicity in the bottom, there are relatively large number of metal poor stars here. So this has been a problem. It's called the D-dwarf problem for a long time. And then to Milky Way, particularly for the solar neighborhood, we have to reduce this metal poor stars. It's not possible to do this other places easily. Maybe future mission like Habitat Observatory might be able to do this in other galaxies as well, but until then, we can't do this directly. The solar neighborhood model is assumed is in-fall. In this case, the red line. The number of metal poor star can be reduced, and then the distribution function becomes narrow enough to match with observation. On top of that, if I include outflow, you can imagine the metals, also gas, is removed. So the star formation rate becomes much smaller, and the metallicity evolution becomes slower. And then metallicity distribution function also shifts to the left side. So by looking at this metallicity distribution function, it's very easy to constrain whether the galaxy was driven by outflow or inflow. One note is if you look at the very beginning phase of age metallicity relation here, in any case, with or without inflow, outflow, the line is already -2, 1% of solar at a very short time scale. So chemical enrichment time scale is anyway very short. That's the reason it's very hard to see the first galaxy even with JWST. So chemical evolution people knew this. This is known. It's going to be hard. Of course, I would like to see it, but it's hard. Okay, so now I'm jumping to the hydrodynamical simulations now. So from this is a zoom-in simulation that will become Milky Way type galaxies later on. It's a cosmological initial condition. So you see small galaxies are appearing initially. The bulge component appear very quickly. So bulge stars are old and also metal-rich, alpha enhanced. And then later on, small galaxies keep on accreting because of CDM. We can't really avoid them. But gas accrete onto the plane later on, and then you will see the disk will grow inside out. So disk is appearing now. So don't have so much time, so I'm gonna, after this, not so much exciting, just minor merger, lots of minor merger is happening. So in the simulation, the small scale physics, star formation feedback, identical to all gas particles. Even though the resultant star formation history depends on the environment. So if I pick the stars in the bulge or halo, you can see that the distribution is different. Overall, galaxies grow inside out. We can also measure in the simulation how much inflow, outflow happen. And then we found this, if we take the ratio, inflow to outflow ratio, it's more like a universal profile, the independent redshift. So in other words, the galaxy is evolving in a quite regulated way. So we call this self-regulated star formation of Milky Way disk in the simulation. The same simulation, I can show you the now metallicity map. The red is for metal rich on the face on and the edge on view. You can see the gradient. This gradient looks pretty similar. The bottom one is observation. This is observed Gaia. It's 500,000 of particles, stars are there in the bottom panel. And then you can see they're pretty similar. Both have a radial gradient and also vertical gradient. So chemical enrichment, again, it's universal, no magic when I start with, but as a result, there is such distribution appeared. When I switch to alpha to iron map, the figure looks very different. Gaia also have this alpha to iron observation, and that's the bottom one. So you can see now, radial gradient get very weak. So on the disk plane, most of stars are low alpha, while there is a strong vertical gradient. So high halo stars are high alpha. And in this particular line, there is a bar here. So along the bar, the gas keep on coming in and star formation happening. That's why in this map, there is a low alpha, blue bar appearing in this simulation. The same quantity in a different coordinate that you have seen many times. On the x-axis now, Fe over H, y-axis is alpha to iron, oxygen to iron in this case. This is now not one zone chemical evolution. This is hydro simulation. Inhomogeneous chemical enrichment is ongoing. So there is no one-to-one age metallicity relation. So this is a very important difference from one zone to hydro simulation. Having said that, the basic feature you can see, there is a high alpha plateau, mostly enriched by type 2 supernova and hypernovae. Around Fe over H -1, there is a decreasing trend by delayed enrichment of type 1a supernova. 1a produces mostly iron, so this quantity decrease. This feature is already seen with one zone model Ryan also showed already. In hydro case, we can see the statistical distribution of stars along this relation. And you will notice there is a bimodality here. There is one peak, high alpha peak, and the bottom one, the strong red peak. So in the simulation, I've seen this many years. And I even tried to remove this bimodality myself, but later on, large-scale galactic archaeology survey found this bimodality, and this is really happening in this simulation. You can also see some small number of low alpha stars at the low metallicity side as well. This is also happened in a one zone. No, not a one zone, but in a hydro simulation. So the simulation, this is a 3 years simulation that Harry was mentioning earlier. But all elements are in. So this is another version of the periodic table. Each little figure shows X over E, F over H diagram. And then you see bimodality is everywhere. So even gold one, there is a gold rich, a thick disk star, and a gold poor, the thin disk star. This kind of things also exist. Anyway, future galactic archaeology survey can be compared to this kind of theoretical prediction. So my postdoc Federico Sestito analyzed even more detail. So this is Milky Way simulation, but actually we also have satellite galaxies as well. So he looked into the satellite galaxies and followed the merging history of each satellite galaxies. So these satellite galaxies, this blue, there is a clear mass metallicity relation, but we also found the little scatter along the mass metallicity relation is caused by how much fraction of stars coming from other galaxies. So ex situ component, yellow, have slightly lower bottom part. So this ex situ component around satellite dwarf galaxies are interesting. These are 3 example satellite galaxy elemental abundance patterns shown, and this large scatter is caused by these ex situ stars. So this is a place probably we could find the signature of population 3, the first star enrichment. So I have only 10 minutes now, so I'm going to move on to this now, cosmological large-scale volume. So simulation itself is much bigger, but I'm highlighting the central part that will become the most massive galaxies in the run. So the AGN is also growing at the center. The very last moment, there is a metal puff up red one. That was the AGN-driven winds. So I would like to run once more so that you can see this color is metallicity. So it's very inhomogeneous everywhere. And along the filament, there's already super solar galaxy appearing. And that's a very strong galactic winds caused by supernova-driven winds. And these enriched matter fall onto the central part again, and the chemical evolution keeps going. So how much matter is ejected by winds? So we quantified this in the cosmological volume. We embedded this parameter to trace the metal loss fraction from individual galaxies. And then we saw that most of galaxies have slightly negative value, meaning most of galaxies gain metal from outside. But this red one is more pinched populations at low mass n. There are more low mass galaxies lost metals by supernova-driven wind. Small number of massive galaxies also lost quite a lot. 20% of metals produced inside the galaxy is driven away by AGN-driven winds. So in terms of metal loss, both processes are important. However, if we calculate this mass metallicity relation, the impact of AGN is pretty small. And then we found back then, this is more than 10-year-old, decade-old simulation. But we found this metallicity distribution evolution is pretty mild. Maybe we had a hint of slope change at metal poor end. We didn't see for a long time before JWST, but maybe this may be happening at very low mass end. Newer simulation we also have. My former PhD student, Diana Ibrahim, changed feedback description of this cosmological simulation with 4 different ways of injecting supernova energy. In this case, the metallicity, mass metallicity relation changes, particular evolution of that changes, and then from them, it should be able to constrain the modeling of feedback in a cosmological volume. Radial gradient is good at low redshift, but maybe at high redshift, the gradient is a little bit maybe too steep compared to the observation. This is related issue. So I don't have so much time, so let's jump on to this nitrogen to oxygen ratio. Just to remind you, from now, we are looking at high redshift galaxies. We would like to see high redshift galaxies. Iron is not accessible, so let's look at nitrogen and oxygen ratio. Low metallicity, there is a plateau, and at high metallicity, there is an increasing trend. Increasing trend is caused by metallicity dependence of nitrogen yields in all stars, plus delayed enrichment from AGB stars. The plateau one, so this simulation did not include rotating massive stars. So this plateau is already produced by inhomogeneous enrichment from AGB stars only. If people are running one zone calculations, one zone people cannot get this plateau without rotating massive stars. And then previous work was saying rotating massive stars nearly equal Wolf-Rayet stars are important to explain this plateau. But back then, 2018, we said we don't need rotating massive stars. I was happy also that this also matches very well with the local relation. But we got this. And then, okay, I should accept the rotating massive stars are important. So now partially using Riemann-Dickieff yield, that they are calculating the rotating massive star nuclear synthesis yields as a function of metallicity and rotational velocities. The green areas are Wolf-Rayet stars. You can see with rotation, green becomes everywhere. However, there is a problem. If I just use this Riemann-Dickieff yield, I cannot reproduce Milky Way observation. That's the green line. So this is pointed out by quite a few chemical evolution people. Particularly carbon to iron ratio is much higher. Nitrogen may be okay, but another element, iron peak elements are very off. The iron peak elements are off because they don't have hypernova. Carbon is an issue. But this is the element we would like to use to understand high redshift observation. So we can't use the Riemann-Dickieff yield as it is to study high redshift chemical evolution. So now I have another version of a model based on my own 2020 nuclear synthesis yields, but I added envelope from Riemann-Dickieff one, so that's the blue line. Also, I also include another type 1A supernova from Chandrasekhar explosion as well, so that's the magenta line I'm going to use in the next slide. But this was already mentioned particularly for GZ11. I said Wolf-Rayet stars, assuming standard IMF, can reproduce observed very high value of nitrogen to oxygen ratio if I assume intermittent or dual starburst. And then later on, people found similar nitrogen emitters at low redshift, and then people also measure argon oxygen to argon ratio as well. These combinations are very important, and then I have only one slide to explain in 2 minutes. The same figure. So nitrogen to oxygen, local relation is here. With in-fold model, it's possible to get more or less this blue line. So blue line is not just smooth in-fold, but it's intermittent in-fold is assumed. So that's why this zigzag line appearing. But anyway, galaxy evolve along this line. Observational data occasionally appeared above this area, and this area can be reproduced by outflow. So if I include a bit of outflow, the line moves to orange, and a strong outflow becomes even higher. So the reason is, with inflow, hydrogen is increased, so the line goes to the left. Outflow, oxygen is selectively lost in the calculation. It's not assumed by hand, but it's naturally happened. So the line goes up, and therefore, more bursty star formation galaxies appear above this relation. Very similar argument for oxygen to argon as well. So basically, oxygen to argon is a proxy of alpha to ion. So it's plateau and decreasing trend. But the same model with outflow model appears below the Milky Way type self-regulated star formation. So I think this is the indication of these galaxies are not self-regulated. Something happening. Combination of inflow and outflow. This is already suggested by Daniel quite a long time ago, but I am making the model now to explain this. I think I'm done. So galaxies are on the track, other galaxies are off track. And then I am just going to show the conclusion and take a question. Thanks very much for listening.
Thank you very much, Jackie. Are there questions? Ricardo?
Yes, I have a question. Very nice talk. The last models, not showing the inflows and outflows. With these models, can you say something about the amount of gas, mass of the inflow that is needed to dilute metallicity, to move the metallicity from 3.5, say, to X?
If I have a multiple element, it should be. So only with nitrogen only, various parameters are degenerated, so I cannot. And then even with argon, still there is a bit of degeneracy. But more elements will help, carbon particularly.
But compared with the mass of the neutral gas of a typical low mass galaxy, they are comparable or are these kind of things?
Okay, so gas fraction was high toward the bottom part when star formation is active. And then the nitrogen is, in this case, coming mostly from HB stars. So when gas is used and star formation becomes lower, nitrogen is enhanced. So toward the up, gas fraction tends to be low.
Any other questions for Jackie? Please, go ahead.
Yeah. Very nice overview. So if I understood it correctly, you cannot live without fast rotating massive stars in the evolutionary tracks, right? So recently, there has been the tendency that at least the initial rotations of massive stars are not as strong as, for example, Geneva or Longi and GFV predict. Is that a problem for you, or yeah?
I guess so. So what I'm doing is just take this yield, and these elements come from sometimes wind, sometimes the carbon nitrogen synthesized inside the star and ejected together with supernova. That's also included, both components. And then when I take as it is, carbon is overproduced. So carbon production should be suppressed somewhere during winds, or helium core doesn't get exposed, or during explosion, a lot of material go back to black hole. So something, or convection also may help a bit. I actually don't know where is the problem, and but we actually clearly know we need more nucleosynthesis years with rotation and explaining Wolf-Rayet population correctly.
Thank you very much, Jackie. If you have other questions, please post them on Slack or find Jackie later. So let's give her another round of applause. Our next talk is from Eduardo Mendes, who is giving a virtual talk. Eduardo, can you see us? Wait, maybe I have to mention.
Yes, I can see you, but I want to know if you can see my screen.
Yes, we can.
You can see the change in the slide, right?
Now we cannot see it anymore.
Well, let me just make sure that I'm doing the right thing here. Let me see if now. I think it's a. I'm gonna try to just share the PDF. Sorry, I think sometimes we have a problem with this. All right. Can you see it now?
Yes, but it's not full screen. Can you put it full screen?
I think so. Sorry.
If you go to view.
Yeah, sorry. Enter full screen. What is
Okay,
it now?
thank you very much. This is great. Yeah.
Yeah. All right. So sorry for the technical problems. Luckily, they were solved. I'm Eduardo Méndez Delgado. I'm a tenure track researcher at the Instituto de Astronomía at the National University of Mexico in Mexico City. And today I would like to talk about several issues that make our sleeping worse every night, as I summarize here. I know everybody were thinking at some point, is the case B of recombination valid in ionized nebulae? As some other previous talk were also mentioning, are the nebulae really thermally uniform? And the most important ones, because we actually saw a lot of discussion on the chemical evolution models and the implications based on the chemical abundances that we infer. The key question is, are the nebular abundances that we infer correct? And this is something that is, of course, related with some of the biggest issues that we have in the nebular abundances studies. That is that there is a well-known abundance discrepancy factor. And essentially, if you derive the oxygen abundance or the carbon abundance, as Kelly Page mentioned this morning, with recombination lines, you get a different result than what you get when you do it with the collisionally excited lines that are the brightest ones and that are the base of the so-called direct method. So essentially, this is a problem because then we wonder which are the correct abundances, if there are any of them. And of course, we would like to know why they are not consistent. What is the physical problem that we are not addressing correctly and that may be present in many places of the universe? And as I mentioned here, if you take into account that some of the explanations to the abundance discrepancy problem is, is the I was just checking some comments in the chat, but now I see that there is no problem. One of the most accepted possible solutions to or possible explanations to this problem is the presence of temperature inhomogeneities, given the fact that the collisional excited lines are exponentially dependent on the temperature, while the recombination lines are linearly dependent to this quantity. But of course, that implies that we have a systematic bias. We may have a systematic bias in our chemical abundance determinations. So this is something that we would like to address with more and more data in order to see different aspects of each possible explanations to this problem. And I think that one of the key elements to understand this abundance discrepancy is the helium atom. As everybody knows, helium atom has two spin configurations. One is the triplet configuration and the other is the singlet configuration. So why this element is because it's one of the most simple ones. In principle, the singlet configuration of helium is quite simple. Their atomic data is well known, but there are two basic assumptions that may play a role here in the emissivity of the lines. Of course, you have to take into account that for having a recombination line, you have to have enough population in each level in order to trigger the decay and give rise to the emission of the lines. And this is essentially testing the case B recombination for helium, because in the case of the singlet configuration, the base level is actually a singlet one, so it's connected to the higher levels. And of course, the higher levels are also dependent on the temperature structure. So if we get the ratio between several lines of the singlet helium, we may see the dependency of the recombination case B and the temperature structure of the gas. So this is what we wanted to get. This is what photoionization models predict if case B is operating correctly and there are no thermal inhomogeneities. So this is what we wanted to get, but this is what in reality get with several data. So essentially what we found is that if we infer the temperature with this singlet system of helium, we have a very strong systematic difference between what we get with collisional excited lines, the 4363/5007 that we use for everything. And this problem or this systematic difference is stronger in the systems with lower metallicity or higher temperature. And of course, this is assuming that the case B of recombination is operating. But if we actually use other lines in order to make a stronger test with a model that consider also deviations from the case B towards a case A of recombination, we still have this discrepancy in most of the objects. So there is a systematic deviation that we are having. Several talks in this morning actually gave some light of why it's important to understand helium abundance, and in particular the primordial helium abundance. So essentially understanding all the physics that it's involved in these systems is crucial, is key. We may be tempted to say, well, recombination lines of heavy elements are too faint and too problematic, just they have a problem. But it seems that other recombination lines, in particular helium lines and hydrogen lines, are also having very interesting physics that we don't understand totally. So two physical explanations can give an explanation to the figure that I showed previously. And it's likely that both affects case-based deviations because of the absorption of hydrogen or even the escape of photons that are able to ionize the circumstellar medium in helium are deviating the population of some levels, and temperature inhomogeneities may also play a role in this effect. So both effects are likely to be present, and because both are present, we would like to have more tests and more studies on this regard. So essentially, if we have two different chemical abundances, both with recombination lines and collisional excited lines, we would like to have an independent test in order to know which are the correct ones. And I think that the Galaxy is the best laboratory for this, because essentially we are able to test what is happening with stars with oxygen, direct oxygen determinations of young stars that didn't have time to actually change the chemical composition of these stars. And since these stars are actually very young, they should be comparable with what we get with the interstellar medium in H2 regions. And if we use radio recombination emission from hydrogen to infer the temperature and infer metallicities, we can get a very huge range of potential metallicities from 7.5 to close to 9 in a very wide range of galactocentric distances. And we can test if the metallicities that we get with temperature inhomogeneities and without temperature inhomogeneities are more likely to be consistent with the stars. And this is something that I did with my student, Rafael Martinez Hernandez from the National University of Honduras. And what we find is that including the temperature inhomogeneities actually make the H2 regions consistent with what we get in stars in direct comparisons of oxygen abundances. So stars are indicating metallicities that are higher than what we get with the direct method that considers a temperature, an homogeneous temperature structure. And essentially something that we also test, and this is something that it has been discussed also in previous talk, is that it's important to have a result map of the ADF. And this is something that we did in this Low-Metallicity digital survey local volume mapper collaboration, something that a very nice project that I've been working on. And we have resolved map of several galactic H2 regions, and we are, for the first time, covering the entire H2 region, something that only has been done in the galaxy with planetary nebulae. And what we find is that essentially the ADF peaks in the place where the temperature of oxygen 4363 also peaks, and that the ADF is not homogeneous in consistency with also other plots from Kelly Page this morning. So it peaks actually closer to the ionizing source. So there are several implications for the high redshift universe. Of course, if we don't understand correctly what's happening with the physical conditions, essentially we don't know correctly if we have a bias in the chemical abundances that we may get. And in particular, there are chemical anomalies that are important for us, in particular the nitrogen over oxygen. But are we sure that they are chemical anomalies or not something that is based on a poor understanding on our physical conditions? And something that was mentioned also in the morning is that we need to calibrate strong line methods for high redshift galaxies. And something that we would like to know, I think, first is that do we really need a different calibration for high redshift galaxies, or we need actually more statistics to get this a good representation of all the physical parameters that we may have. This is something that we present in a paper from Rosales Ortega. This is something that will be discussed in Carla's talk. So I just mentioned that because it's important. Most of the excess in nitrogen over oxygen comes from a particular ion. The nitrogen 3 times ionized that comes from the UV lines. So understanding the precise physical conditions of this volume is key. So I'm just going to leave my summary, and thank you very much for listening to me.
Very much, Eduardo. There is time for questions. Questions for Eduardo? Danielle?
Hey, Eduardo, this is Danielle Berg. Thank you for the very nice talk, and phenomenal to see those spatially resolved recombination line, collisionally excited line temperatures. That was incredible. Lots of information, so it went by fast. Are the temperature differences in the spatial variations enough to match the discrepancy?
This is a very good question. Well, it's a bit difficult to see or to translate temperature variations in the map, in the plane of the sky, I mean, with the temperature fluctuations or temperature variations that we may have in the line of sight, because essentially it depends very much on the geometry and the amount of ionized gas that you are integrating in every spaxel. So the best example of this, I think, is the study from Odell and from 2003, Odell et al. From 2003, where they actually test the temperature variations with the Hubble data in Orion. So this is the highest spatial resolution that we may get so far in this sense, and essentially it seems that even under those circumstances, most of the temperature variations are included in the line of sight. So qualitatively, it matches with the sense that we see increases in temperatures and we also see peaks in the ADF, but quantitatively it's quite difficult to say.
Very quick question, please. Yes.
Couldn't be this difference between the line abundances caused by inhomogeneities in density instead of temperature?
That's perfectly possible. There is actually there are some degeneracies in the emissivity of some lines between density and temperature. There are several talks that mention this, the Daniel Berg's talk and some others were actually addressing the importance on understanding the density. There is also a very nice work from Alessandro Marconi with this code called Home Run that actually includes a more complex density distribution that actually explain part of the temperature variations that we may have, but it's difficult to disentangle if both parameters are in degeneracy.
Any other questions, you can post them on Slack. Let's thank the speaker again.
Thank you very much.
Thanks. Cool. I guess I can test. Can people hear me?
The next speaker is Maud Gall, and she will talk us about metal poor massive binaries and binary products in the local group. Thank you very much.
Yeah, thanks for the introduction, and thanks for the organizer for this really awesome conference so far, and also the opportunity to talk to you all today a little bit about my ongoing work on metal poor massive binaries and binary products in the local group. And so I usually start out motivating why we should study metal poor massive stars, but I don't think I have to do this in this group as much. And I'll go right to why do we have so many uncertainties when we try to connect metal poor massive stars to all these components. And that is, if we look at the field about 8 years ago, we see that really in this lowest metallicity regime, we didn't actually have a lot of empirical constraints with high enough quality data to do quantitative measurements. And it's only now that we're starting to really at least fill in that lower right quadrant. And I'm really excited about the Tempest results and Elisa Schuster's work that's going to fill out the space even more. And to just also highlight our poster child Galaxy here, right? It's the only local galaxy that really allows us to fill up that upper right quadrant and really constrain the stellar physics in this yet observationally basically unexplored regime. But today I'm going to focus specifically on binarity, and to put everyone on the same page, I'm kind of going to define some of the configurations I'm going to use throughout the talk. You can find binaries in detached systems. So in this case, they will only gravitationally interact with each other. They can be in semi-detached systems. So one star fills its row slope and is transferring mass onto its companion. Or it can be in a contact system where now both stars are filling their row slope and exchanging not only mass, but also energy. And so these two configurations are really interesting because they will alter the stellar evolution perhaps the most. And so questions that I'm interested in answering with my science is, what is the fraction of metal poor massive stars that is in binaries? And also, what are the characteristics of the overall binary population at low Z? And so we can turn to higher metallicity environments, and we've seen versions of this plot before. But essentially, in higher metallicity environments, we've seen that massive stars prefer to be in binaries, and about 78% or so of them will go into one of these interactive stages at some point in their lifetime. However, the SMC is not really representative of truly low metallicity environments, and beyond the SMC right now, there is no systematic study of binarity in the metal poor regime, which is why this space is empty and a big question mark, right? And so, unfortunately, I'm not going to put a new data point on this plot just yet. I'm working on it hardly, but instead, I'm going to showcase some examples of low metallicity binaries that we've discovered so far. And so, I'm talking about a contact binary system in WLM, and I'll talk about some binary interaction products in LEOA. And before I start with WLM, I just also want to, again, contextualize for people who don't work in the local group a lot, why it's been so hard to look at these galaxies. So if we scale them to what they look like on the scale compared to the SMC, you can see that's a little bit smaller, I would say. However, it provides a really nice opportunity here, because that means you can use HST imaging and cover your galaxy in a couple of pointers instead of like 5,000 that it would require for the SMC. And so other people have looked at WLM with time series data, except not for binaries. That doesn't mean, though, that we can't actually kind of utilize this data to our advantage. And so I scavenged the archives for eclipsing binary at sub-SMC metallicity. And here is a picture of WLM, which was studied to understand the RR lyrays in this galaxy. And so if I take this image and make a CMD out of it, and highlight our system, you can see that from the CMD alone, there's nothing suspicious about the star. And this is also perhaps why a lot of binaries are actually hiding in our CMDs, and perhaps impacting our results. It's only once you get to the time series data that you see there's a nice eclipse. And so this is already phase folded by the period, but the data was taken over 3 days. And additionally, I was really lucky that Carrie Gilbert here for her UV program also looked at this galaxy again. And so we add some additional constraints in the UV, although only 1 data point. And then I was also very lucky that an ERS program took very deep photometry of this galaxy, meaning although I cannot, it's actually not a time series program, you can use the individual exposures as time series data point. And so this light curve here is actually, even though it's phase folded, it's continuous observations of that same spot and giving us a very tight constraint on the shape here of our eclipse. So this is all, again, all pretty qualitatively. So now we want to get some quantitative information out of this. And so I used a neural network to emulate Phoebe, which is a really great light curve modeling tool, to constrain some parameters of this system. And so in black here, you see the median line, or fit, sorry, to the data. And in color, you see random draws from the posterior distribution. And so the system is consistent with 2 pretty hot stars in minimal contact, meaning both of them just overfill their Roche lobe. However, the lack of the coverage of the secondary dip and the UV data gives us some wiggle room here, so that actually there's no statistical preference towards a contact system or a semi-detached system, which is why this is just a candidate. In the context of all the contact binaries we know in the LMC and the SMC, we also, maybe not surprising, are right kind of at this cusp between semi-detached and contact system. And so why is it actually important to understand whether this is a contact system and what its actual mass is? It is because the mass distribution here, depending on what your input in your stellar binary evolution, can reproduce different mass ratios. And so it's a crucial test, actually, for our binary evolution models to obtain the mass ratio distribution of such systems. And so I have an RV follow-up program. Currently, we only have 1 data point, so no RV curves just yet, but stay tuned. I also want to point out that I've discovered another 20 or so of these eclipsing massive binaries across different low metallicity environments, and we'll have an undergraduate student working with me this summer on characterizing those. But because the selection function and the completeness function are very hard to quantify across this data set, we're still really much in need of a more systematic, dedicated study to these systems. And to highlight what this would look like, I want to highlight some work by Cheyenne Chariot, who's a graduate student at Caltech working with me, where we're doing this at the high metallicity end. So we don't talk about this too much in this community, but on the plot, higher metallicity than the Milky Way also didn't have any data points. And so this is actually work that's really only possible with HST, which I know we've said this before, but like submit white papers to give our body a little push. And I'm really excited about these results because I think this will be applicable to many dwarf galaxies within our reach with HST. Now I want to transfer over to, I guess, mass transfer products. So you have 2 massive stars here, where the slightly more massive star is going to start to evolve and expand faster. And so it's filling its Roche lobe and transferring mass onto its secondary, which starts to gain in angular momentum due through the mass and really spin up until it's spinning really fast and even perhaps has a little bit of a disk here. And we're left with those 2 binary products. And so we've heard about these throughout this week as well. I'm just reiterating the definition here. So we have a BE star and a strip star. And I'm actually really interested in knowing how these products may look different at low metallicity. And so this is the lowest metallicity sample of spectroscopically identified BE stars that we have so far. And you can see, there is some clear clues that this scenario of binary mass transfer, we might be onto something here. We have high rotation, so that washes out a lot of the typical helium-1 lines we actually use to characterize those stars usually. You have the broad emission in the Balmer lines. And I also pointed out that 5 of the 7 BE stars here are actually not near any major H2 regions. There's a little bit of observational bias in there, but them being out in the field is interesting for other reasons as well. There's another clear clue that this could be actually BE stars, and that's in the photometry here. So if you look at the UV CMD, they kind of appear mostly on the main sequence, but as we look into the optical, they start shifting really onto the blue helium core burning sequence. And so this IR shift is predominantly due to the disk contributing some IR access to our photometry. And so I do have an HST program that is trying to explore how many of these stars show this behavior at different metallicity, but there's some indication that this effect increases as we decrease with metallicity. And now I'm going to switch to the other star, kind of conveniently showing a very similar behavior on the CMD, the green star right here, which is namely our strip star candidate. And so in the last couple of years or so, we've really seen this field start to bloom, where we've discovered many of these strip stars in the SMC. And so here we have an isolated star, meaning actually just the strip star dominates the spectra. And you see this steep helium-2 absorption line really indicating that this is a hot star. We have the ones where they have a B star companion, so we see the helium-1 in absorption here as well. And then some of them have those strip plus BE star, where again we're seeing this infilling here of the disk. This is a much higher resolution than the spectra I just showed you, so you can actually see the double peak feature, which is typical of disk emission. And when we look at our strip star candidate in Leo A, well, it looks quite a bit different, right? We have really strong helium-2 emission that, based on some of our fits, suggests there's a broad and narrow component. We have basically no helium-1, but I will say, this is maybe signal-to-noise of 20 or so, and if this companion is rotating really fastly, we would probably not see the helium-1 absorption feature here. And we also have H-beta in emission. And so if we get the stellar parameters of the system and put it on an HR diagram, we do see something really interesting, where the basically isolated or fully stripped stars are in this left corner here, and the strip stars plus BE stars are in the upper corner here. And we fall kind of in between there. So maybe our star was not as efficiently stripped as some of the other strip stars that make it all the way down here. And so we're perhaps dealing with something like a partially stripped star here. We do see some RV variability in the data that we have, but we currently don't have enough of a constraint on these to actually get an orbital solution and get a full constraint on the companion. However, we can look at the photometry. And so if I only fit a strip star model here, I do miss all of the optical and the IR. If I invoke really high dust, I don't match the UV anymore. So you have to fill in a secondary component. And so the data seems to be consistent with both either an extended circumstellar material or with a smaller B-type star and some circumstellar material filling in. And so, TBD what the true nature of this is. And so I'm going to leave you with my summary slides.
Thank you very much, Maud. Any questions for Maud? Questions online? Questions in the room? No questions? I am not an expert in this field, but I was wondering, for Can you say again, for how many stars can you, I was interested in the fact that you noticed these differences between the SMC and the lower metallicity. So can you comment more on that and how many more observations we need to understand better what's going on?
I mean, right now we really just know of this one LEOA system. I will say, I think in NGC 3109, there is also a kind of peculiar emission line system that I think Abby Mintz has mentioned in her paper. But yeah, there is also, I would say, dedicated helium-2 searches for these types of systems. But as of right now, this is the only one we really have full spectra for from. I mean, I didn't show the UV spectra, but there's also UV.
This is really interesting. Questions? One quick question. Oh, sorry, I didn't see this.
Oh, it's okay. You said my favorite word, so I'm curious about the dust. Do you see any reddening or in this circumstellar potential EE product, or is it just the suppressed UV?
Yeah, I mean, I think dust is really hard to constrain here because we don't exactly know if there's a companion and if there is a companion, what the nature of the companion is, because the spectra is otherwise pretty blank. And so getting a stronger dust constraint from this star would be hard, but maybe if you look at the ones surrounding it, you can do a little dust map and see. I will say the dust overall in the OA, as you probably know, is quite low. So I'd be surprised that we suddenly have crazy dust. It's in the middle of nowhere to start.
It's huge, like that's several orders of magnitude.
Yeah. But.
Okay. Thank you very much. If you have other questions, please put them on Slack. So let's thank the speaker again. And our next speaker is Katie Sharp. And wait 1 second. Katie will tell us about probing isolated dwarf galaxy evolution with JWST spectroscopy analysis. Thank you very much, Katie.
Thank you. Yes, hi everyone, I'm Katie Sharp. I'm a third-year graduate student from UC Berkeley. And before I start, I'd also like to thank the organizers for setting up this excellent conference and also for having me. I'm very excited to tell you today about my ongoing research studying isolated dwarf galaxies using JWST stellar spectroscopic abundances. So I normally like to start this talk by giving a background on why we care about dwarf galaxies, but luckily most of the heavy lifting has been done by the fact that everyone here has decided to come to a low metallicity conference, and dwarf galaxies are, of course, low metallicity environments. So hopefully you're all interested in them. I particularly am interested in dwarf galaxies as test beds for galaxy evolution physics. So these are simple populations. They typically only have one or a few stellar populations in them, and thus can help us get at kind of like the base unit of galaxy evolution. And conveniently, we also have numerous dwarf galaxies in our very local universe for which we can study a variety of parameters and also environments that they live in. I use galaxy spectroscopy to study these dwarf galaxies in detail. And when I say galaxy spectroscopy, there are a few different things you might think of, including ones we've heard at this very conference. If you have an unresolved, for example, a high-redshift galaxy, you typically put just a single slit over the whole galaxy and get one spectrum. If you have one that's a little larger on the sky, maybe it's semi-resolved, you can put an integral field spectrograph on it, such as the JWST IFU. But if you have a sufficiently high-resolution telescope and also a near enough galaxy, you can go even farther to the point where you're resolving individual objects in this galaxy. In my case, individual RGB stars. From these individual stellar spectra, we can extract chemical abundances and radial velocities. And we've already actually seen this plot a few times at this conference in various iterations, including earlier today during Chiaki's excellent broad talk. Essentially, early on, we have a lot of alpha that is produced by type 2 supernovae. So these are the products of helium burning, and you get this high alpha over Fe, alpha enhanced or iron depleted ratio, take your pick. After a delay, we have the turn on of type 1a supernovae, which produce more iron. And so you start depleting this alpha over iron ratio moving down this track until you reach eventually some sort of equilibrium. And as successive generations of stars are formed, they're locking in their birth chemistry at the time of their birth, and thus populating along this track, forming this characteristic alpha Fe diagram. This is also very sensitive, in addition to the two type of supernovae I mentioned, to other processes that cause changes in chemistry on the similar timescale, so things like inflows and outflows. Once again, we heard this earlier during the review talk. If I move away from my little cartoon here, we can go to galaxy chemical evolution models, and you can see that there is a difference between when you vary the inflow rates and the outflows. So on the left, I have varying inflow rate, and on the right, I have varying outflow strength. And you can see that these produce very different tracks in alpha and Fe. And these, you are able to fit these galaxy chemical evolution models to your observed points, your star points here, to figure out what set of parameters fits your galaxy. The picture is a little more complicated when you have multiple populations or you have very complex star formation histories, for example. We see this in the Milky Way with the alpha bimodality of the disk, two populations, thin and thick disk, and in the Milky Way dwarf satellites, which have very bursty, complicated star formation histories. But with your combined alpha and iron elemental information, you are able to still fit these chemical evolution models and determine a very detailed picture of how the galaxies evolved. And this has been done in great detail for the Milky Way system, thanks to large surveys such as Apogee. However, on the converse, this has only been done in the Milky Way system, and that's just due to how easily accessible these stars are. I really liked modes like zoom out and zoom in to show how tiny on the sky these isolated dwarfs are. They are much more crowded and much more faint than our very easily accessible satellites. And so we have paucity of data. This does lead us with a biased picture of dwarf evolution that is shaped by the satellites, which themselves are subject to environmental processing. So you can strip the gas from these satellites in such ways as room pressure and tidal gas stripping, which can cause the galaxies to quench, regulating star formation, etc. But how do you regulate the star formation in an isolated dwarf galaxy? Well, there are secular processes that could and should affect almost every galaxy. I've crossed off AGN and reionization because our local dwarf galaxies don't tend to have AGN, and also they often survive reionization. And that leaves us with these main mechanisms, which are feedback-driven outflows and inflows. And luckily, that is exactly what these galaxy chemical evolution models can tell us. So to answer this question of how isolated dwarf galaxies evolve, we have a Cycle 2 JWST program using near-spec MSA spectroscopy in 3 local group isolated dwarf galaxies. These are thought to have never interacted with the Milky Way or Andromeda. They're all at about 1 megaparsec and are less metal-rich than the SMC buzzword there. These were chosen based on their very different star formation histories. So if you look at my cumulative star formation history plot on the top right, Leo A is this very recently star-forming system. IC 1613 has this intermediate constant star formation, and Tucana is quenched. And luckily with JWST, we are able to get high quality and large enough samples of RGB stars in all 3 of these dwarf galaxies. About 70 per galaxy. Today I will be highlighting results from Leo A and Tucana. First, we're going to take a look at one of our brighter stars, this one in Leo A, and look at the spectra. So these are the 6 exposures of this one star in Leo A. I'm skipping over all of the data reduction for time, so please feel free to come talk to me if you're interested in JWST spectroscopy. Yeah, we perform a full spectrum fitting, and we're jointly fitting to all 6 of the exposures simultaneously instead of stacking. And this is due to undersampling and the fact that the spectra are a little too low resolution to stack robustly, at least in the current iteration. This is really hard to see anything on, so let's take a little zoom in of this region that has a bunch of lines in it. And you can see that our red model is actually fitting by eye these observed lines fairly well. So that's already a great indication that we're probably doing a decent job in extracting these elemental abundances. Okay, now I want to emphasize that the next slide is still preliminary and might be subject to change. But here we have the alpha Fe diagram from LEO-A. This is about half of the stars in the sample. I have made a very conservative quality cut for this talk. If I draw a line to guide the eye, this is the shin, which is the slanted bit on the cartoon. And this is pretty much exactly what you would expect for a dwarf galaxy. In fact, LEO-A has had previous observations from the ground. They were subject to pretty high uncertainties and thus not super useful for detailed modeling. But I'll show them to you to say that this is like pretty much exactly what we expected for LEO-A. So JWST probably doing a very good job in getting individual stellar elemental abundances. Right, now I'm going to plot Tucana on the same figure. It's a little less straightforward, but I will once again draw lines to guide the eye. And this seems to be indicating that Tucana has 2 alpha sequences. I was really surprised when I first saw this. I thought that I had messed up my fits somehow, but I think this actually should not have been very shocking to me. Tucana photometrically has long had evidence that there are multiple populations. It's interesting that these populations would be on very different alpha sequences, and that would be indicative that they probably evolved somehow separately. My first instinct was that this could be a merger, an ancient merger, because Tucana is relaxed in the present day. So you had 2 smaller dwarf galaxies, each with their own sequence that came together, and then we see the 2 sequences remaining as fossils. It's also possible that these could both be in situ populations. Savino 2019 found that Tucana has 2 ancient star-forming epochs separated by about 1 gigayear. And so you could have had one sequence form from the first one, break some sort of change in chemistry, and then the second sequence formed from the second. This is still speculation. I'm really excited to do the detailed chemical evolution models to see what scenario could have caused this pattern. With my last 1 minute and 24 seconds, I would like to talk about what I think is the most exciting part of JWST's ability to do these abundance patterns. So let's zoom out from the local group to the local volume because we're going to need it. I've talked to you already about these 3 isolated local group dwarfs that we have. But JWST lets us go to crazy distances for individually resolved stellar spectroscopy of 5 megaparsecs. That's not very far astronomically, but when you think about resolving individual stars and getting their spectra, that is very far. And this opens this massive reservoir of a bunch of galaxies that we could study. We've heard, even at this conference, about all of these really cool, really metal-poor dwarfs that are just outside the local group that we could now study with JWST. And we can go into even more crowded regions. I gotta go real fast. These I'm pubbing because these are 2 programs that I am co-I on that I will soon be working on, looking at the crowded disk of M31 and the stellar halo of our nearest massive early type galaxy of Sen-A. Even though this isn't low metallicity, M31 is very interesting as it gives us another example of a massive disk galaxy. So we can determine whether this bimodality I've mentioned before, which we think is linked to disk formation physics, if that exists outside of the Milky Way, which would be cool if true. And then in Sen-A's halo, we also expect very metal poor stars. It'd be very interesting if we could discover any extremely metal poor stars, but we think that halos of galaxies are very metal poor. But also the chemodynamics that we can study here will tell us about whether our theoretical understanding of how massive elliptical galaxies form is correct. And I am so out of time, so I'm just going to leave my conclusions up and take questions.
Katie, are there questions for Katie?
Thank you for this talk. I was just curious, are there any known today satellites with alpha element ratios as low as the second branch you see in?
Yeah, oh, I already have that on this slide. I don't believe that I've seen any that are that low. Maybe someone in Apogee in the audience could tell you more, but I think that this is very alpha de-enhanced. Yeah, it would be interesting if, I mean, these are still preliminary results, but it'd be really interesting if that was true and we could get this like unenhanced of alpha.
I have a very quick question about SNA that you showed at the end. I don't know if it can be important, but SNA as an AGN, so I don't know if this will change something in the picture or because you're looking at the halo, so maybe.
We're not able to get very far into the galaxy because it is very crowded. This is like the closest in you can get, and even then you're really pushing it in terms of crowding limitation. I'm not sure. I think that there's a lot of work that's been done on AGN and how they affect their galaxies and also the halos. It would be interesting if we could find something.
Other questions? Over there, yeah.
Thank you so much for the nice presentation. If I understood correctly, when you plot the points, I mean, can you go to the last slide?
Oh, yeah.
Because it's the summary. In Leo A, you have this kind of, it's telling you that it's mostly driven by outflows or inflows, right? I mean, the points in there, in terms of the enrichment that you can see.
Yeah, the slope.
Yeah.
Yeah, it's driven. There's many factors that can drive the exact slope. You can increase or decrease the slope based on your outflows and inflows. It also is affected by the IMF and the star formation history and the delay time of supernovas. So there's a lot of factors, but you're able to determine, like, by using these galaxy chemical evolution codes.
I bring this up because I belong to more like the gaseous phase of the ISM, and there are very nice maps of H1 that may tell you something about I don't know what is the kind of instabilities produced by these inflows or outflows. Maybe they not match the same angular resolution, but maybe they help. It's part of the little things, so you can, the little things survey. So in case you want to inspect that from the cold ISM, it would be a very nice.
Yeah, that could be really interesting to look into as well, in conjunction with it.
Perfect. Let's thank Katie again. As always, I remember that you can post another questions on Slack. And this is. And now we have a talk from Patience Su about the nature of high-redshift nitrogen-enhanced galaxies, AGN or starburst. Please, Pei-Xin, the floor is yours.
Hello, everyone. My name is Pei-Xin Zhu. I'm a fourth-year grad student. Fourth year grad student from Harvard University, working with Lisa Keeley. Today, I'm gonna switch the gear back to nitrogen emitter again. But mostly focusing on whether these galaxies host AGN or not. And this work is done with collaboration with James Tressler, who's there, and Lisa Keeley and Tiger over there. Before I start my presentations, may I ask you all questions? Do you think AGN are important at high redshift? Please raise your hand if you think so. Okay, that's great. But why don't you talk about AGN that much in the conference? That's something surprised me. Good. So you all think AGN are important, so I don't have to convince you. But I'm going to argue that AGN are actually important nitrogen emitters. So the study kind of, the starting point of this study started in 2023 when the first few JWST spectrum of high redshift galaxies comes in. And then at the time, I was visiting Daniel Berg in Austin, and then they were talking about this impressive spectrum. specifically because the nitrogen booming nitrogen lines in the UV spectrum. And then at the time, like the class C spectrum is also out. And most interestingly is that you don't actually see the UV nitrogen emission lines in most of the class C galaxies. But why are we seeing those in those high redshift? And there seems to be an argument of like these are nitrogen enhanced galaxies. And then people start to look at what is the ionizing sources in these galaxies. And the typical way to do that is to overlay these high redshift galaxies in this UV diagnostic diagram or BPT diagrams. And then you're trying to compare and see whether they're closer to AGN model or star forming model. And if you look at GNZ11, which is the brown yellowish point in this diagram, you find that from the left two plot, you're thinking that they're closer to AGN model grid. But then if you are looking at the right plot, of course, they're locating far away from the AGN model grid and actually is closer to H2 regions. So then it causes some contradictions of what exactly these galaxies are. And why don't that kind of diagram doesn't work? Well, mostly because the assumption evolved in those photonization model people has been using for a long time was not appropriate for these populations. The most important thing is the nitrogen abundance assumption, of course. So the gray square is highlighting where those high redshift nitrogen emitters locate in this nitrogen abundance diagram, as you have already seen multiple times in this conference. And on the other hand, most of the current model, photonization model, is actually assuming a local scaling relations. And all those local scaling relations.
The mic, like a little bit higher. Maybe.
How about this? Yes. Okay. And most of the photonization model used by the community of most popular are assuming a local scaling relation. And this local scaling relation is built up on many years' time to observing the local galaxies. And they are actually a significant mismatch in the model assumption and the data. So we want to tackle this. The solution is that we build a set of photonization model that actually tailor to the abundance as seen in this nitrogen emitter. And then with that, we can answer whether these star galaxies are AGN or star-forming galaxies. So after explorations, which I will save for time, for the 2D diagrams, which we usually tend to use, we found that these equilibrium width-based UV diagrams are the most effective in terms of separating AGNs and star-forming galaxies. And now you're seeing the models with normal nitrogen abundance, or it's like assuming a local scaling in the nitrogen abundance. And the blue model grid here is AGN model, and the red grid is star-forming model. And to be mentioned that the star-forming model is already the hardest star-forming model. So the sulfur, stellar radiation continue you actually are moving toward the right. And once we overlaid the nitrogen enhanced model in this diagram, which now the nitrogen abundance is like in log scale minus 0.1. If you read the diagram, this is almost the upper end of what we are seeing now. And the high nitrogen abundance model actually all shift toward the upper right corner of this diagram, which is expected because in the y-axis, you're having the equilibrium width of nitrogen lines, which are proportional to how much nitrogen you have. And the x-axis, you're having using a lie ratio, which is nitrogen emission line fluxes over helium-2. And helium-2 is sensitive to how hard your radiation field is. That's why most of the AGN model actually locates toward the upper left corner, comparing to the stellar model. So then we can actually draw two division lines in this diagram. That being said, the dotted emission line are characterizing the upper limits of H2 model. So then every galaxies or observed spectrum above this dotted line are actually AGNs because your stellar model cannot reach there. And on the other hand, the dashed line is characterizing the lower limits of the AGN model. So anything to the right of this dashed line, you cannot reproduce by AGN model. So then unfortunately leave a composite region or overlap region, which you cannot tell is there a mix of both excitation source or is it intrinsically only one excitation source, but they unfortunately falls into this region? And let's overlay the high-redshift galaxies. Interestingly, out of the 4 that have both sufficient emission line signal-to-noise detection of this emission line, only 1 of them locates very clearly in this, for sure, AGN region. And 3 of them actually locate in this composite region. And if you actually look for a large sample of galaxies, this phenomenon is quite common at high redshift. That leaving that we are usually run into this ambiguous zone where we cannot really answer with 2D diagram what are the excitation sources in these galaxies. Is that all? Well, I guess you can also write a paper about that, but I'm figuring out that since I'm a grad student, I have more time, I should probably dig into further. So what else we can dig further for those ambiguous galaxies? Recall that we are actually having the full spectrum of these galaxies. So you not only have these 3 or 4 emission lines, but you actually have a full spectrum, including all the emission line and continuum information. Can we do something about that? Yes. If we include the emission line fluxes of all the UV all the way to optical, whatever you can detect in your spectrum of the galaxies, and then also include the equivalent width of the particular UV emission line fluxes. If you combine all those information you can obtain from the JWST spectrum for individual galaxies, and then you compare with the model to see which model fits the best, you can actually find out the best fit model for each individual galaxies. And this is giving a very, in this plot, all the data points are the observed spectrum with the arrow bar, like observed arrow bar. And then all this shaded area is the best fit model. Why is it a shaded area instead of a line? Because we allow a very small variation in either the metallicity, ionization parameter, or gas pressure, which account for because you're only one spectrum for the whole galaxy. And you actually have some variation in those ISM property. So with the combination of all those information you can get, we can actually answer what's the best fit model. And then we drew out a table of this best fit model. On the right is the match fractions, basically how much property is matched by this model. And you can see that the reproduced fraction is like all above 80%, which is quite impressive if you have done the work before. And for the 8 galaxies that we study, which are high redshift nitrogen emitter, interestingly, we find 7 of them are actually best reproduced by AGN model. AGN are important for nitrogen emitter. That's my argument, and that's why I'm arguing for that. And the other thing is that our best fit model can also reproduce constrain the ISM property, and all these ISM property are very consistent with the direct measurement if you account for all those caveats of direct measurement properly. And the other thing seeing is that the gas pressure, the ionization parameter, are actually quite high comparing to all those low redshift value. If you have studied low redshift galaxies before, then the gas pressure or density is almost like 5 to 7, and all those high redshift galaxies are going all the way up to 9 point something in the gas pressure. And the ionization parameter is also frequently going above minus 1.5. So 2 things from this study. First, AGN is important. Second, if you don't have the enough resolution to do all those direct measurement and accounting for all the caveats, you might consider using this photonization model kind of fitting to do the best fit model. This will give you also a consistent constraint, and you can do it this way. And this will also help to constrain like whether they are AGN radiation or like purely star formation. And then from all those ISM property we get, we think the most likely nitrogen enriched mechanisms is superstar clusters. Whether it's the Wolf-Rayet stars, very massive star, supermassive star, I don't know. Yeah, but then we'll leave you questions. Does it mean that AGN are associated with the nitrogen emission, nitrogen enriched mechanism itself? Well, not necessary. And it also linked to a question of why are we seeing like why all the nitrogen abundance we measure from these high redshift galaxies using UV lines are yielding such a higher ratio. It's mostly a detection limit. So from the same figures you were seeing, now I'm plotting the detection limit of Sears survey and JWST deep survey, which is, for JWST is like 28 hours exposure. And the detection you can get for JWST is like somewhere around here, which means that you actually don't reach down to all those nitrogen normal, like local nitrogen abundance galaxies at high redshift. So you're not seeing all those nitrogen lines in those normal galaxies. So you're actually only seeing the tip of the iceberg, which is the very strongly enhanced in nitrogen abundance. And the JWST archival data, which I just pulled out from the public archival, also prove our detection limit calculations. And the question is, if you really want to go down that deep to detect those nitrogen emission line in those normal galaxies, how deep exposure you need? 500 hours is an optimistic estimation for the bright galaxies. So if you read some literature with the stacking spectrum, some stack spectrum goes all the way to 1,000 hours, and they're yet still just reaching somewhere around here, not really down to the normal abundance. So it's challenging. But AGN are important, so don't ignore AGN in your high redshift study, and thank you.
Are there any questions? Over there. Christy?
So it looks like you are constraining the AGN peak energy. Is that enough to tell you anything about the AGN itself, whether it's intermediate mass black holes or supermassive?
Yeah, that's a very good question. So actually, if you look at those epoch value, which is not in this slide, but the epoch value are actually quite low comparing to the local redshift Seyfert galaxies. So for local redshift Seyfert galaxies, it's usually minus 1.5. But for these high redshift galaxies, it's going all the way down to minus 1.9. So this is, I would say, it's favoring the intermediate black hole cases, but also like because the epoch is determined by both the black hole mass and accretion rate. So the lower accretion rate you have, or the more massive black hole you have, or you are not in the thin disk accretion regime, but like in the thick disk accretion regime, that will all give you a lower like epoch value. So this is telling us what that is.
Ricardo, you had the question. Ryan?
Yeah, thanks for the nice talk. So I was basically wondering if you've tried composite models instead of just AGN or star forming, and I think GNZ11 is a good example because it has oxygen too, but you have UV doublets that indicate densities as high as 10 to the 9, and you have to have two phases or else.
Oh yeah, so these are all constant pressure model, so they actually account for the density variations in the model itself.
So what are the ranges on the densities you put here?
So these are just, so if you read the paper, there's like notions of these are assuming a fixed temperature, and then you convert to these fractions, this value. So what we are actually constraining in the model is the pressure.
So in an object like GNZ11, does it span 10 to the 9 to 10 to the 3 in density?
So the density profile in the model is actually gonna range from all the way the highest value in the most inner regions, and then going down at the boundary. So those O2 lines are usually, we interpret them, they are emitting from the boundary, which the density is low. So that's why we always argue that you should use constant pressure model instead of constant density model, because the constant density model cannot account for these variations. And if you look at the best fit diagram, like they are actually consistently reproducing those highly ionizing lights and those like lower ionizing lights.
Does it reproduce the doublet ratios of the?
No. We didn't check the doublet ratio. But the doublet ratio are used to constrain the density, and the density is matching what we are deriving from the model.
If it's very quick, Alberto.
I was just curious to know what were the assumptions that go into your conversion between nitrogen equivalent and your spec exposure time.
Your spec exposure time?
Yeah, when you show your limits of exposure.
Oh, these are so it's like assuming a rest frame continuum level, which are derived from this nitrogen emitter, like bright galaxies. So that's why I say it's an optimistic estimation. So if you're actually using a fainter continuum level or fainter galaxies, you actually, the detection limit is going to go up.
Take scene again. As always, please post other questions on Slack. And now we have the last talk of the session, that is a virtual talk from Carla Rillano Cordova about tracing the chemical evolution of galaxies with the CNO abundances, new constraints at redshift higher than 6. Carla, can you share your screen?
I think
Hi,
I'm sharing, right? Yeah.
We only see a white screen.
Sorry. Can you see now? Can you see now?
No. Can you try
Matilde,
to unshare and share again?
Yeah, I shared the entire screen for that.
Okay, sorry, Carla, it was loading, but it's just slow.
Okay,
So
there is.
try again, please.
Okay, this is now.
We can wait a second, maybe. Yeah, we can see your desktop background. So maybe you have another screen that you are.
Oh, probably. But, If not, we can share my in the computer. Sorry for that.
If this doesn't work, worst case scenario, I can change the slides for you. But,
yeah.
Should I? Okay.
Yeah, please.
So wait, but now this is not connected anymore. Okay, it is.
Yeah, thank you.
Okay.
Okay, thank you.
Go ahead, Carla.
Yeah, thank you. I'm Carla Rillano Cordova. So thank you very much to organizers for a very nice conference. Sorry for the technical details. So I will present a sample or two samples that have been working to investigate the chemical enrichment of galaxies. Next, please. We have here also so different plots about the chemical abundance patterns between the different elements. So it's really very nice that we can see so these interesting results. So in the bottom of this figure, you can see these abundance patterns. So in principle, in the local universe, we have a study or analysis, some of these different abundance patterns. So, but now with JWST, we start to populate all these different abundance scaling relations. So we are having very interesting results. So Thomas, Noah, early this week show all these different plots. Next, please. However, I will focus in this talk in nitrogen and a little bit of carbon. So just a reminder, nitrogen is produced for two different types of stars, intermediate and massive stars. And this element is released to interstellar medium in different time scales. So here you can see pictures of Chucky that is really very nice. They show these tiny scales. But also nitrogen is produced to different components. One is primary, it's secondary, and depends on the initial condition of the gas, the seed. We saw many of these discussion also already during this week. Next. But the important thing is that all these processes are imprinted in this plot. And this plot tells us to understand the star formation history of the galaxies. One thing that you can see in this plot is like the different dispersion that you can see, and there is really very high, even at all the metallicities, low metallicity, high metallicity. Some of the dispersion is intrinsic and depends on these processes that I discussed before. But also there are other mechanisms that help us to understand or are proposed to understand this dispersion. This is like water stars, discontamination, shocks, HEN, or feedback. So next. So we also have these very high nitrogen enrichment objects that I will speak a little bit later. So next. So in this talk, I will focus on two different cosmic epochs. Next. One is the using XS with a redshift around 5. That is basically a study, we will study there the carbon and nitrogen abundance, but also we will connect these high redshift galaxies with Glassy, that we have different information about the physical properties. These two surveys are already presented before. Thomas did a really nice work introducing XS and other Glassy and different tools already. And finally, I will introduce a new methodology to derive the metallicity in galaxies with extreme physical conditions. Next. I will start with XLs. And as you see here, there is a very nice spectrum from different emission lines. For XLs, we detect two galaxies with simultaneous detection of carbon-3, nitrogen-2, and also oxygen-3, 4363. That allow us to determine the chemical abundances with temperature. So we also derive the different physical properties during the via ECT modeling. So next. And one of the first steps is to see the ionization source using the BPT diagram, and also to correlate these physical properties with the different samples of the literature. So as you can see here, the sources are very well related with the bulk of the observations from other studies in the literature. Next. So now I show you here the carbon and nitrogen abundances derived from this optical spectrum, and I add here different local star-forming galaxies and also Lamin continuum emitters. So some of these Lamin continuum emitters are Greenpeace galaxies. And one of the results that we had with these high-redshift galaxies is like these galaxies are relatively high metallicity in comparison with other galaxies that you see here for high redshift. We also notice that these galaxies are nitrogen enrichments, while carbon is keeps similar that related with the nucleosynthesis with I predict for Corcolat supernovae. So to try to understand what is causing these nitrogen enrichments, we use chemical evolution models in collaboration with Chucky. So next. For these models, we use the observations to constrain these models. We vary the INF, and the results are here in this plot. So one of the takeaways is like these observations can be produced for a standard or bottom-heavy INF. And this means this nitrogen enrichment that is primary is likely to intermediate mass star. However, we still need to account for other sources for more increase the sample to try to corroborate these results, and also to try to minimize the uncertainties of the carbon and nitrogen abundances due to the ionization correction factor. In general, in Excel, we also have another galaxies with nitrogen. I think Dirk will explain this a little bit later. So next. But now to try to connect these high redshift galaxies with local star-forming galaxies, we can see again this plot, and you see that in principle, these high redshift galaxies are cover the parameter space that these local star-forming galaxies are. So to try to understand these dispersions, I compare the Glassy with different properties. And this talk, I will just focus on star formation rate and feedback. And next. For star formation rate, this plot have been studied in different studies before. You can see here the references, but basically using strongline methods. Here we have just electron temperature measurements, And as you can see here, the star formation is correlated with natural overall, implying ongoing star formation actually contribute to the natural enrichments. But this is in the classic galaxies that have big epoch, and the AGB stars still contributes. But also you can see that the high redshift galaxies align to this distribution, and also the very high redshift galaxy 6. Next. And there is a work from Alex Cameron that shows similar relationship here. If you focus in the purple symbols that are the TE abundances, you see how this external or additional sample also correlate well with the findings for class A. So, but also as we are having this high star formation rate, this implies a lot of gas to form stars, and this is related with the outflows. So if we can see in the another slide. Okay. Yes, the next slide. The next one, please. Yeah. So we compare here with outflows and using the UV absorption lines to compare with natural overall. And you see there is a moderate trend between the outflow and the natural overall. We also add the density, and seems to be a little bit of gradient with these different properties. Now, to try to understand the strengths of these outflows, we calculate the mass loading factor, and you see here in the next plot. So in this plot, you see an anti-correlation with the natural overall in the mass loading factor, indicating that peak path for stellar width becomes relatively weak at natural increase. And this is more for the massive star-forming galaxies. So we can interpret this like gravitational suppression of feedback. So it was really very interesting to talk with Chucky. So maybe I need to talk with you, Chucky, in some point. So, but we want to continue this investigation about this outflow in correlation with natural overall, but now using emission lines in the optical to see that it is a discrepancy. So this is also shown better in early this model. And next. Okay, this is my summary takeaways for these two topics. With Excel, we explore the chemical enrichment of high-redshift galaxies, specifically at 5, and we found that at these H's, or these redshifts, we are start to see the contribution of intermediate mass star. So also with class C, we are seeing, comparing all these different properties, we found that the dispersion of this relationship is probably an interplay between electron density, feedback, and star formation. And next. Finally, I want to introduce a new methodology to derive the physical conditions of chemical abundances NX in galaxies with extreme physical conditions. So we use for this methodology these 3 different emission lines from the same atom, and we use the 43635007 as a density indicator instead of the temperature. And this is thanks to the high critical density they have of these diagnostics. I am using this method in this example. This is a galaxy that had been mentioned early, this week by Danielle. And you can see what is the cross of this light ratio is the density and temperature for a high ionization zone for this galaxy. In the dashed line, the red dashed lines you see is the assumed electron density, the token 2024, used to calculate the electron temperature. So these differences that are critical have an impact in the chemical abundances that you derive from high-redshift galaxies. Next. So we apply to this methodology to additional 5 star-forming galaxies with these high conditions. And the first thing that we found is that using this methodology, the inferred metallicities are 0.29 dex higher than previous determinations, but also align with these derivations that other studies have when account for the high density gas. In the case of the nitrogen, when we use our methodology and we calculate nitrogen 2 plus and oxygen 2 plus, we had closer values than the local star-forming galaxies, meaning that probably this is not natural enhancement. However, our method can have limitations and caveats, and we want to increase the number of these kind of objects. Please, if you have this kind of objects, talk to us. We really want to try to improve this methodology. So next one. So thank you very much, and this is my summary.
Carla for the talk. Are there any questions? Online questions? Ryan.
Hi, Carla, it's Ryan. Thanks for the really nice talk. Yeah, so this method using all the O3 lines simultaneously is really cool. But of course, the 1666 to 4363 will be really sensitive if you have any dust, and especially if you have very steep dust curves in the UV, as we know can happen in a lot of low metallicity sources. So I guess, did you try assuming different dust attenuation curves, and how much did it change the results for the inferences?
Yeah, thank you, Ryan. This is a really very good point. Yes, of course, this is one of the limitations that we have, but basically one of the galaxies, for example, show anomalies reddening corrections. So we try to use first what the information we have from the literature, instead now to try to see to comparison homogeneously with the literature. Of course, it will be other, analysis to try to see the reddening is important. We have also in the paper this limitation, of course, but also I want to say that it also depends on the atomic UV data that we are using. Yeah.
Thanks.
So, can the people who are presenting flash talks start to come here while we read a question from online? Carla, when you talk about stellar winds becoming weaker at high nitrogen overabundance, do you mean the outflow rate is lower as a consequence?
I think it's less stronger, probably, that, or there is some way mechanisms that are mixing there before launching. This is my thought.
Well, thank you, Carla. Let's thank the speaker again. Carla on Slack for any further questions, and here we'll start with the flash talks. I give you microphone. You
I
have
one
the microphone.
here.
Great.
Yes.
Okay, 2 minutes.
Okay, thank you. Hi everyone, my name is Erik Andersson. I'm a postdoc research scientist at the American Museum of Natural History in New York City. And I want to take this opportunity to just highlight 3 papers that I've been working on in this project that I call Edge Inferno. These 3 papers are highlighted behind these the summaries, and I also included QR codes for 2 of the papers that are already published. The project that I've been working on, this Edge Inferno project, is a project where I've been simulating dwarf galaxies at the ultra-faint dwarf limit. And the key novelty of these simulations is that I'm resolving individual stars in these simulations. Critically, I'm getting all the stars down to 0.5 solar masses as individual particles. And this means that feedback is resolved on a star-by-star basis across an entire Hubble time. The 3 papers cover slightly different topics. The first one focuses on mock observations, and basically the main conclusion from this paper is that complex light profiles can result in biased characterizing properties such as V-band magnitude and half-light radius when estimated from magnitude-limited star-by-star photometry. In the second paper and the third paper, I focus more on chemical enrichment. The second one focuses on internal uncertainty. This is things like chemical yields and sampling of the IMF. And the third one focuses on external factors, such as assembly history and environment. How much time do I have left? 30 seconds. There we go. Yeah, for the second one, about these internal factors, the assumptions around type 1a supernova seems to be the ones that are most uncertain for these systems. But I see a lot of stochastic variance, especially when it comes down to the sampling of the IMF. And for the assembly history, I do see that assembly can drive pretty distinct chemical populations, but abundances alone are probably not enough to disentangle these. So, thank you.
Thank you very much. Next, we have Nishant Mishra.
Yep.
This is right.
Is it the middle button for the?
Oh,
there we go.
Yeah.
Okay.
And you have 2 minutes over there.
Hi, everyone. My name is Nishant Mishra. I'm a graduate student at the University of Michigan, and my work focuses on understanding metal enrichment in the circumgalactic medium of dwarf galaxies. And so what we know from literature, as Sean mentioned earlier this morning, is that the metal budget of dwarf galaxies prior to our most recent work was about half full, consisting of the cool 10 to the 4 Kelvin inner CGM phase, as well as the ISM and the stellar component. And so what our work has shown is that you can fill the rest of the metal budget of these dwarf galaxies by looking in this warm, hot, highly ionized oxygen-6 bearing phase. And so what we showed in our most recent work is that as a function of column density, you have lots of absorbing gas both in the inner CGM and in the outer CGM. And you can use this kind of simple order of magnitude formula to compute and estimate a total metal mass associated with this phase. And so if you do that in measuring in kind of annular radial bins, you can get basically a very coarse mass profile for the CGM of these dwarf galaxies. And you can find 2 takeaways. So first, you find that the inner CGM and the outer CGM both contain significant metal mass. And the combined metal mass of both of these bins is something like a few 10 to the 6 solar masses. And so when you have a mass, and the mass range of these galaxies is something like 10 to the 8.4. So we basically effectively closed the metal budget of galaxies in this mass range. And if we want to think about physical conditions, so up till now there have been 3 already published measurements of the chemical enrichment properties of the CGM of dwarf galaxies. And our focus most recently has been trying to understand the chemical enrichment in the outer phase of the CGM. So that's this outside the Virial radius. So in this example system, we have a dwarf galaxy that's about 100 kiloparsecs away from a nearby quasar, and we see strong absorption in multiple metal lines. And using this, we infer from photoionization modeling the chemical enrichment properties. And what we find is it's a chemically enriched system whose metallicity is actually similar to the expected ISM metallicities of this mass range of galaxy. And when you compare it to the other systems we found in literature, so you can match the colors to the different metal instruments, you find that the chemical enrichment patterns of dwarf galaxy CGMs is varying widely. You have almost a 1.5 decade variance in metallicity and a 1.5 decade variance in NONO. And so what that tells us is that the CGM is both a large metal reservoir and it's very chemically inhomogeneous. If we want to understand or do any chemical enrichment modeling of dwarf galaxies, we need to take into account the circumgalactic medium. So if any of that interests you, please come chat with me over coffee.
Thank you very much. So we have Connor Painter.
Thank you.
Please go ahead.
Hi guys, my name is Connor Painter. I'm a graduate student at the University of Texas at Austin. From JWST observations, we know that at high redshift, star clusters can reach extreme densities, high masses, and higher mass fractions of their host galaxy than we see in the local universe. I am analyzing a new simulation called Campfire to help connect these observations with theoretical models of stellar feedback and cosmology. Campfire is part of a suite of unreleased fire simulations run by postdoc Jenna Samuel at UT Austin. You can come ask me about the details of Campfire later, but for now, all you need to know is that it forms hundreds of galaxies over the redshift range 20 to 9, and in each galaxy, we have sufficient resolution to form star clusters down to 10,000 solar masses and 1 parsec in size. What we find is thousands of gravitationally bound clusters. 70 to 80% of all star formation in the box occurs in bound clusters, and we find them in 2 distinct formation sites. 85% form as normal substructure in more massive galaxies, but the other 15% form isolated at the center of their own host dark matter halos. They're both single stellar populations that form in quick bursts, but the cluster-like dwarf galaxies have distinct distributions of masses and metallicities. We find that before about redshift 16, cluster-like dwarfs dominate the stellar mass in the box, but then become subdominant at later times as massive galaxies build up and form tons of ordinary clusters. We calculate tons of other properties, masses, metallicities, survival times. If any of that interests you, I'll be around. Thank you.
And last but not least, we have Ali Ahmad Kostovan. So please go ahead. You have 2 minutes.
Sure. So I'm Ali Ahmad Kostovan. I'm from University of Kentucky, and I think I'm the guy between you and coffee. So we're going to wrap this up quickly. All right, so I work with Ryan Sanders, who gave an excellent talk this morning that we all saw, and I'm happy to be here to talk about, very briefly, about our recent work with the Aurora survey, where we made measurements for the mass metallicity relation and fundamental metallicity relation, based solely just on the direct TE metallicities. So Ryan talked about Aurora survey and the exquisite data that we've been working with. And for this study, we used a subsample of 34 galaxies that had detections in both the O3 auroral line as well as the O2 auroral line. Now, what's really useful about that is one is tracing the high ionization zones, the others are low ionization zones, and when we look at it in the scope of a MZR plot, your O3 aurora lines are pretty much more towards the lower metallicity, lower stellar masses. Your O2 aurora lines are more biased towards higher metallicity and higher stellar masses. So combining both, you're actually getting a wider dynamic range to constrain OH and stellar mass and wide dynamic range of OH and stellar mass to constrain MZR. And one of the main implications that we got from this, besides that we made a nice measurement for the MZR, is when we compare it to strong line calibration MZRs, they're very much consistent with one another. And that really tells us that calibrations that are based on local analogs of high-redshift galaxies, they're doing a pretty good job of recovering OH when compared to our direct TE MZR. And that has implications for planned surveys in the future with Roman, for example, that will have great access to these strong emission lines. So in the future, using such calibration, we could even do statistically good measurements of MZR and FMR with statistically large numbers. And in the last few seconds that I have, we also made a comparison with simulations, which is not very easy to do because each simulation has its own yield assumptions and so forth. So we tried our best to bring everything to the same normalization at about redshift of 0 and see, well, how the slope and trend everything looks like at redshift of 2. And overall, the slopes are pretty much consistent, but none of the simulations were able to reproduce the same normalization. That doesn't mean that simulations are wrong. Observers, we also have other caveats as well in terms of selection biases and what exactly, direct TE metallicities are exactly tracing, multi-zone ISM, for example. And I don't have much to talk about FMR right now, but you may come and ask me any questions. I'm here for the rest of the conference. Now you can go to coffee.
Again, the speakers of this session, let's give a round of applause of all the speakers. We are coming back at 3:45, at 3:45, and please check the posters from Ezra's UK and CWK in the cafeteria. Thank you very much.
Yes, by construction.